Hello and welcome everyone. So in the last video we looked at intrinsic semiconductors and I explained how electron-hole pairs are created at the same time. That is, an electron is created, a free electron is created at the same time as a hole is created for intrinsic silicon, and we also defined N and P to be the concentrations of free electrons and holes respectively, and we also defined the term N times P equals Ni squared, where Ni is the concentration of intrinsic carriers. So it's the concentration of intrinsic charge carriers, and that's N and P. That's Ni is equal to N, and Ni is also equal to P. And so in this presentation, we are going to look at how we can change the structure of the silicon crystal in order to change its conductivity properties. So in the previous video, we looked at the structure of crystalline silicon, and we saw that each pair of silicon atoms share two electrons between them, and that they form the covalent bond. So this is a covalent bond here. Actually, let me remove these dots here because they will confuse us by electrons. So this is a covalent bond. This is another covalent bond, and we saw that in this crystal we have covalent bonds, and two silicon atoms share two electrons between themselves. And we saw that one electron can leave the crystal and can start to wander around. This electron can start to wander around, and so on. This electron can come here, and that's when one electron leaves and a positive charge is created on the silicon atom. We have a hole created here, and at the same time this electron will start to wander around as a negative charge. And so the electron is a free electron, a negative charge, and the hole here is also a free hole that can move around, and it is a positive charge. So if we look at the periodic table here, we have carbon here and we have silicon here. We have also, note that for carbon, silicon, germanium, and so on, we have four. It's in the group 4 in the periodic table, so we have 4 valence electrons. In this column, the last, we have boron, aluminum, and gallium, and they have 3 valence electrons. And here, nitrogen, phosphorus, and so on, they have 5 valence electrons. So what would happen if we took one of the silicon atoms here and replaced it with a boron atom, for example? So let's draw here. Let's redraw. Let me just, please bear with me, and I will just redraw a crystal of silicon here, and we'll replace some of the atoms here with boron atoms. So this is silicon, and this is silicon. Now here we replace this with a boron atom. This boron atom, and here still silicon. And now silicon, let's count 1, 2, 3, and 4. So 1, 2, 3, and 4 electrons. Now boron would have 3 electrons. So we have 1, 2, and 3. So notice here, notice what happens. Let me just finish drawing the silicon here. So I'll just draw. So it's 4 electrons per atom like this. I'll just finish drawing so we have something to work with here. Now, this boron atom also has only 3, 1, 2, and 3 valence electrons. So look what happened here. Because boron only has 3 valence electrons, what we have created here is a vacancy. There's no electron here to form the covalent bond. So there's a space here, and also here there's a space. And so what will happen? The first thing that will happen is one of the silicon atoms, well, all of the silicon atoms that can, they will take one of their electrons. For example, this electron will abandon the silicon atom and it will end up here. This electron will abandon the silicon atom and will end up here. So I'll draw this electron here, and the electron from the silicon atom is going to disappear. So this electron disappears, this electron disappears, and when it disappears, then the vacancy has moved from the boron atom to here. So from the boron atom to here. Notice that before, in the boron atom, it had a vacancy, but it was still neutral, because every atom is neutral, so the same number of electrons as protons was here. So everything was fine, everything was neutral within this atom. But the moment one silicon atom gives off its electron to the boron atom, the first thing that will happen is the boron atom itself will have a negative charge here, and the silicon atom will have a positive charge here in this vacancy. So same thing here, there is now a negative charge here, and there is a positive charge here on the silicon atom. So this positive charge on the silicon atom is called a hole. It's a hole, it's a positive charge and it's a hole, so hole plus. This electron here is called a bound charge. Bound charge, and it is negative. Same thing here, this is a bound charge, and this guy here is a hole plus. Okay, so what does this mean? The first thing is, this boron atom, it has a negative charge, but this charge cannot move. It does not move. Once the electron left the silicon atom and went to the boron atom, it becomes a bound charge, a charge that doesn't move. However, the hole that it has created here, this hole can move, because other electrons can leave the other silicon atoms here. For example, this electron can come here all the way and fill this gap here, and then the hole will have moved into here. So now we have a hole here, a positive charge, and here before it was positive and now it is neutral. So the hole has in effect moved from here to here. So let me draw the arrow. The hole has moved from here to here, and the electron has moved from here to here. So these holes, they can move. Now this hole can move, for example, from here to here and so on. And so this hole can move, and it's also a charge, so it's a charge carrier. However, the electrons here, they do not move. Unless in normal circumstances, these electrons are called bound charges. They just stay there and they do not move, they don't contribute to charge carrying. Now, I don't know what happens if you raise the temperature. If you raise the temperature more and more and you start to melt everything, then this electron is probably gonna leave, and the crystal structure in the first place, it will melt away. And so you will destroy the crystal structure if you melt this. And so the electrons are going to get unbound and it's going to conduct more electricity and so on. But while it is a crystal lattice, in normal circumstances, in low temperatures, this is going to be a bound charge and it does not contribute to charge carrying. Okay, so now that we have this, so we have doped, so this is doped silicon, and we doped it with boron. Boron has 3 valence electrons, so if you take a boron atom like this, so you have the atom like this, you have the inner electrons that don't take part in bonding and so on, and then you have 1, 2, and 3 electrons around the atom like this. So you have 3 valence electrons. So 3. And so we take these boron atoms and we put them inside the crystal lattice by some means. And once this happens, then we have created charge carriers called holes. And these are positive charge carriers, and they move from one place to the other. So the holes are called majority carriers. So majority carriers, and this is what they call. So they are majority carriers because they carry the majority of the charge and currents on the atom here. I'm just increase the size of this. Okay. So now the other thing we have to look at here is just a simple formula and a simple way to find what are the respective concentrations of electrons and holes on here. So we're going to define a term which is P sub P. Remember, I have to tell you that this type of doped semiconductor is called P-type. P-type semiconductor, and this is because we are creating positive charges or positive holes, positive charge carriers. Sorry, not positive charges on the crystal lattice. So this is P-type. So for P-type semiconductors, we defined a variable called P sub P, and this is the concentration of holes. Concentration of holes here. We still have Ni, which is the intrinsic concentration. And so what we can say is that P sub P times N sub P is equal to Ni squared. And N sub P is the concentration of free electrons for the P-type conductor. So okay, so these are some terms. Now another term is ND, or sorry, Na. For P-type is called Na, and this is called the concentration of acceptor atoms, or in this case it's equal to the concentration of boron atoms. And why is it called the concentration of acceptor atoms? And this is because once you put a boron atom here, this vacancy is going to accept an electron from the silicon atom. So it's going to take one electron from the lattice, and so it's an acceptor. It accepts an electron. Okay, so we have Na, which is the concentration of acceptor atoms. Now if we take a piece of silicon like this, let me draw here a piece of silicon. So if we take a piece of silicon like this and we dope it with boron, and we transform this into P-type silicon, then there is going to be a concentration of holes. There's a concentration of holes here, free holes moving, and also a concentration of electrons. Now all the free electrons on this P-type silicon are going to be created. So the electrons here, the E minus free electrons are created only by thermal means. So only if you raise the temperature of the silicon, for example at room temperature, there is going to be some number of electrons, free electrons, that are going to escape the silicon. So you have the silicon here, and you have your crystal lattice there sharing 2 electrons between 2 silicon atoms. If you raise the temperature a bit, some electrons are going to escape the silicon, and they're going to create a free electron, just like we looked at in the previous video, and this is going to become a hole, a positive charge, and so on. So for P-type, we are creating extra holes by a different means than thermal means. But all the electrons are still going to be created thermally. We are not adding extra electrons anywhere, so they are going to be created only thermally. They're going to escape the crystal lattice only if you raise the temperature and so on. So if we want to find out what is the concentration of free electrons here, we can use the equation. So we have P sub P, which is the concentration of holes for P-type. Multiply this by N sub P, which is the concentration of free electrons for P-type, and this is still equal to Ni squared. Now if we dope this semiconductor such that the concentration of acceptor atoms is much larger than Ni, which is the concentration of intrinsic carriers, if this is the case, then of course the number of holes, which is pp, or the concentration of holes, which is pp, is going to be just about Na, because the number of holes created by thermal means is going to be much less than the number of atoms, of boron atoms, that you have added to the silicon. So all of the holes, most of the holes are going to come from the boron doping. So you can write that the total concentration of holes is about just about the concentration of boron atoms. Again, because the number of holes created by thermal means is just small in comparison to the number of boron atoms that you have added to the silicon. So you add a lot of boron atoms, so you want to create a lot of holes. So most of the holes are going to come from this. So you can basically ignore the number of holes that come from the thermal the thermal creation of holes. And so if you use this formula, then you can replace PP by Na. So you have Na times Np is equal to Ni squared, and therefore Ni squared, sorry, here. And so therefore the concentration of electrons, of free electrons, is going to be equal to Ni squared over Na. So this is just so you can find out what is the concentration of electrons for p-type semiconductor. Okay, so this is p-type semiconductor. So in the next video we're going to talk about another type of semiconductor doping, which is called the n-type. And for n-type we use an element from this column 5 here. So this column, and as you can imagine, they are going to do the reverse of this type here. For this type we saw that it takes one electron and it creates a hole. So for this type here, you can imagine that it's going to do the opposite and it's going to donate an electron into the crystal structure. So until then, I hope you have enjoyed the video. So please, if you have enjoyed, don't forget to subscribe and so on. And thank you very much for watching.